Okay, I want to talk a little bit about measuring thermal energy, the law of conservation of energy, and how do we actually know how much thermal energy something gains or loses, right? That's heat. So how do we measure heat? How do we measure this stuff? Well, there was a problem that was sort of like this in the homework that I had you guys do. It was number 55 on page 333, or 336, I guess. And it said that we've got a 100-gram mass of tungsten. Tungsten is metal. It's the metal they use to make light bulb filaments. We've got a 100-gram sample of it at 100 degrees Celsius. Okay, so we heated up this tungsten to 100 degrees Celsius, and then we dropped it into this bucket full of water. And this bucket full of water has 200 grams of water that was initially at 20 degrees Celsius. Okay, and we're supposed to figure out how much energy that the tungsten lost, which is sort of, well, it actually asks for the specific heat of the tungsten, but we have to know how much energy it lost to get that. Okay? Now, they tell us one more piece of information. They tell us this thing reaches a final temperature or reaches thermal equilibrium at 21.2 degrees Celsius. Now, I want you to think about what that means. Thermal equilibrium means the temperature stopped changing when we hit 21.2 degrees Celsius. And the reason the temperature would stop changing is because the temperatures of the two objects finally settled on one final temperature. They became the same. So this piece of tungsten has got to give away its thermal energy. It's really, really hot. Energy flows from hot things into cold things. So it gives away energy to the water until they're the same temperature. When they reach the same temperature, then energy stops flowing and heat stops going anywhere. Okay, so if we can figure out how much heat was lost by the tungsten, then we can figure out its specific heat, right? Because Q equals mc delta T. And we know the mass, it's 100 grams, so 0.1 kilograms. We know the change in temperature. It went from 100 degrees Celsius down to 21.2 degrees Celsius. So that's what? Negative 78.8 degrees Celsius is the temperature change. We want the specific heat, and we could get it if we knew how much heat it lost. But we can figure this out. The law of conservation of energy says energy is not created or destroyed. Whatever energy we start with, we have to end with. It can change forms, it can move from one object to another, but it has to stay the same. Okay, well, if we think about this, we know this thing is losing thermal energy. It's getting colder. Okay, so it cools down, but the water is gaining thermal energy, and that water is gaining its thermal energy from that block of tungsten. So if we look at the water, we know the water started at 20 degrees and ended at 21.2 degrees, just like the tungsten. So it had a change in temperature of 1.2 degrees Celsius. Okay? Its mass, 200 grams, is 0.2 kilograms, and we know the specific heat of water is 4,180 joules per kilogram degrees Celsius, or Kelvin. It doesn't matter since a degree Celsius and a Kelvin have the same magnitude, and we're talking about a change, not an absolute temperature. Okay, so we can figure out how much energy the water gained. Q equals m, 0.2, times C, 4,180, times delta T, 1.2 degrees. Okay, we can figure this out. And we know this is identically the heat lost by the tungsten. Now this is true because this is a closed, isolated system. The energy is limited to going to the water. Okay, if we left the tungsten out of the water and it could lose energy to the air, then we would have to account for the temperature change in the air as well. Okay, so what this is called is this is actually called calorimetry. Calorimetry. And a calorimeter is a device that we use to measure thermal energy. It's basically a can with a stirring rod and a hole in it, right? So you can put a temperature probe in there with another can inside of it. Now the reason we have a can inside of a can is so that we can insulate the system. We put our sample and our water in the inner can. The outer can is to isolate it from the rest of the world, to prevent energy from getting into or out of it. Okay? We put the lid on it. We can keep track of the energy inside of it. We keep the energy inside of it. Nothing gets in, nothing gets out. We measure temperature changes, and we can figure out how much thermal energy is transferred from a substance to the water we put in there. Okay, so we're going to use a calorimeter in an experiment. We're going to use a couple different calorimeters. We're going to do a couple different labs. Okay, probably don't have time today, but I want you to be thinking about this. Okay, we know how much energy is in food, and the reason we know that is they give us that energy. The nutritional information gives us energy in calories. Okay, you'll notice calorimetry, calories, they're kind of related. This is from the old school thought that heat was caloric, that fluid, that things, warm things had and cool things didn't, comes from that. But it's basically an old label. Now, calories are different than calories. Okay? Capital C, lowercase c. This capital C really means kilocalorie. So 1,000 calories equals 1 kilocalorie, or 1 capital calorie. So when you have your granola bar and it says it's 120 calories, it's actually 120,000 calories. Okay? It's 120 kilocalories. And what does that mean? The calorie is the old unit. The new unit is based on the SI system, and the SI system uses joules for energy, and it turns out 1 calorie is 4.18 joules. Okay, so I want you to think about how we can measure the energy stored in food. What can we do with it? How can we get that? How can we measure it? And can we check to see if the nutritional label is right? Okay, so something to keep in mind. But while you're doing that, I also want you to work a few problems. Okay, so you're prepared to actually use a calorimeter. So there's some calorimetry problems on page 319. Make that 321. Calorimetry problems, page 321. And what I want you to work is numbers 6 through 9 to try to see if you can figure out how the thermometer, how the temperature probe, how the calorimeter, how the energy changes. All that stuff is not too bad. It's just a few problems, okay? But it's how to use a calorimeter, what a calorimeter does, what measurements you can make, and what you can find. Okay. Good luck with that. Let me know if you have any difficulties, and be sure to get your quizzes handed in.